Suit. Okay, so welcome everyone to the Symmetry seminar. We are restarting after a short break. It's a great pleasure that Thomas Dumitrescu from UCLA will be speaking today on symmetry breaking from monopoles in QED 3. So please take it away.
Okay, so thanks for the invitation and the introduction. It's a pleasure to be part of your seminar. I'm going to be talking about this paper that we put out in October with UCLA collaborators at that point, Luigi Nero and Ryan Thorngren. Luigi is now in CISA, and I'll be discussing quantum electrodynamics in 2+1 spacetime dimensions and its symmetries and how they're realized dynamically. I should also point out that there's nice related work on the same theory, which came out around the same time by Shai and Zohar, which kind of proposes the same symmetry breaking pattern from a different point of view by studying certain dualities. So I think, neither of these are completely without gaps, but I think together they provide a pretty strong picture that I'll try to explain. And there's also some work in progress with all of these people that I might mention at the end. All right, and as I already said, for everybody who arrived a little bit late, please interrupt me at any time. Just unmute yourself and shout. All right, so what is QED in 3 dimensions? QED, and it's important a little bit to be precise because different people mean different things when they say QED in 3 dimensions. What I mean is continuum U1 gauge theory with compact gauge group and Chern-Simons level 0. Time reversal will be important in what I say. And NF flavors of charge 1 electrons, by which I mean Dirac electrons in 3 dimensions. Dirac electrons in 3 dimensions are 2-component spinners. So here alpha is a spinor index, and I'm assuming that there are NF of them. All right. And famously, there's a parity anomaly that says that if k is 0, or if you want k to be 0, that requires NF to be even. So I will always count NF in even units. If you wish, if you want to have in your back of your mind the sort of reduction from 4 dimensions of 4-dimensional QED, then the number of 4-dimensional Dirac electrons is NF over 2. Right? Because in 4D we have 4D Dirac spinors. All right, very good. And as I'll say in more detail later, when this is true, when k is 0 and NF is even, there will be a time reversal symmetry. And I'm just going to assume that these have electric charge +1 under the U1 gauge symmetry. So that's the theory I want to study. There's all sorts of great physics that this theory is related to. I could spend some time reviewing it, but I'm sure depending on what community you come from, you have different motivations for being interested in this theory. And it's also historically sort of been a bit of a toy model for more complicated non-abelian gauge theories because it's strongly coupled. It's QED in 3 dimensions is strongly coupled, but it's still not quite as complicated as QCD in either 3D or 4D. All right, so here's the Lagrangian. F is the field strength. Here are my Dirac fermions. I will always be a flavor index. F is the field strength. So it's about as straightforward as it gets. The fact that we have a U1 gauge field means that F has 2π integer fluxes, standard 2π integer fluxes, although it'll soon be important that F is actually a spin-Z connection because the only charged objects around are fermions of charge 1. So in fact, you can upgrade F, or more precisely A, to a spin-Z connection so that this theory is actually bosonic, right? Because you're gauging fermion number. All right. So the fact that the theory is bosonic means all gauge invariant local operators will have integer spin. And in particular, you can study the theory and its anomalies on 3 manifolds that either do not have a spin structure, or if they have a spin structure, you don't need to explicitly choose it, fix it. All right, so before we get to anomalies and these kind of global issues, let me say a few things about the dynamics of this theory, the kind of local dynamics of this theory. And this theory doesn't really have many parameters, but it has a parameter NF, which can be studied, a discrete parameter. And so it's interesting to ask what the kind of behavior of the theory is as a function of even NF. Of course, NF is 0 is simple. It's just free Maxwell theory. And then we have 2, 4, all the way to large NF. All right. So the only cases where we have complete control are the trivial free case and the large NF regime. Because when NF is large, there's famously a controlled 1 over NF expansion. Right? This is a kind of large N vector model where you have NF fields and you can solve it exactly in the large NF limit. And what you find is that there is a weakly coupled CFT whose effective coupling is of order 1 over NF. And so you can compute reliably anomalous dimensions in the 1 over NF expansion and be completely convinced that in that regime there is in fact a conformal field theory without any symmetry breaking. I haven't discussed the symmetries of the theories yet, but they're all unbroken there. All right. Even the large N limit of the theory is not quite free. There are some theories that acquire a non-trivial anomalous dimension, just like in the ON vector model, the ON Wilson-Fisher model, where there's an operator that has a large anomalous dimension. But apart from that, it's almost free. So this is nice. And that means that there's a conformal window at large NF where things are conformal field theories. And then as you lower NF, the effective coupling 1 over NF becomes stronger. So this is the direction of strong coupling. And the question is, what happens here in this intermediate strong coupling regime? So there we lose control, and we would like to know all sorts of things about the theory in that regime. But the most basic question we might ask is, what's the boundary of the conformal window? So where does the theory stop being conformal? So it's logically possible that it's conformal for all values of NF, so that the conformal window goes all the way down to here. As we'll see, I'll argue that the current evidence seems to be that the boundary of the conformal window is here, although it's far from bulletproof, I would say. So there's an enormous body of work on this question, starting in the early 80s, starting with analytic work, not just the large NF expansion, but also epsilon expansion, also various semi or uncontrolled techniques involving truncated Schwinger-Dyson equations, lattice discussions, and more recently, the application of the conformal bootstrap. So the conformal bootstrap is actually very successful at attacking this theory because it has a lot of symmetries and interesting operators whose quantum numbers we know. And especially the recent bootstrap constraints seem to be tilting into the direction of saying that for NF bigger than 4, so starting with NF equals to 4, the theory wants to be a CFT. And plausibly, though not certainly as always, NF equals 2 is not a CFT. So, in answering this question, I have essentially nothing to contribute. I need to either just postulate a particular scenario, or I need to take input from Bootstrap. But once you take seriously the idea that the small NF theories, NF equals 2, NF equals 2, 4, might not be CFTs, you have to answer the question what they could be. They're not CFTs. So it turns out that essentially the moment you know that the theory is not a CFT, you can prove that it has to break spontaneously some symmetries. So I'm going to assume for the purposes of this talk that the theory with an F equals 2 is not a CFT. And I'm going to discuss symmetry breaking scenarios. So for the rest of the talk, I'm only going to focus on this minimal case. The scenario I'm going to propose also extends to other values of an f. So if it so happens that the bootstrap changes its mind, and maybe in the future we will learn that the theory with an f equals 4 is not a CFT either, then the scenario I'll propose will have a immediate generalization to that case, but that's discussed in our paper. But I'll only focus on the case n f equals to 2a because it's the simplest. Just, the symmetry group will be small and everything will be kind of in your face, but also because it's most plausibly not a CFT. All right. So my fermions in particular, my electrons will be doublets. There will be two flavors. And that's reflected in the symmetry structure of the theory. It turns out that the continuous part of the symmetry group is an SU2 flavor symmetry that acts on this doublet index, I. And then there's also a U1 magnetic symmetry, which is the standard flux conservation symmetry in three-dimensional U1 gauge theories without monopole operators in the Lagrangian. I'll say much more about monopoles in a second. So the continuous part of the zero form symmetry is U2. And importantly, there's this interesting Z2 quotient that relates the center of SU2F with the odd elements of U1M. Any questions so far? All right, very good. So I should say that in addition to that, we also have discrete C, P, and T symmetries. And they will also feature in the discussion. Of course, only two of them are independent, so I'll talk about C and T to the extent that I talk about these symmetries. So let me tell you a little bit about the operators that are charged under this.
I do have a question.
Yeah.
Shouldn't it be spin 3 times SU2F times U1 divided by Z2?
Isn't SU2 the same spin 3?
No, spin 3 for space-time. You can't, if you divide...
No. The theory is bosonic. The theory is bosonic, and...
Wait, you have fermions. I'm confused.
There are no gauge invariant local operators that are fermions. All gauge invariant local operators will only transform in a genuine representation of SO3.
Okay.
In other words, -1 to the f is not actually a symmetry. It doesn't act on gauge invariant local operators. That's why I didn't talk about the spacetime part. This is the internal part of the symmetry, and you can say that the spacetime part is just completely factorized.
Right, but if I were looking at the field content...
Yeah, when you look at the field content, it looks like spin
I
3 is
would
acting.
spin 3 times SU2 times U1.
So this is related to my comment that the U1, the dynamical U1 gauge field is actually a spin C connection. That's related to the quotient that you're after. Because when we're talking about the fields, which are not gauge invariant, the electron fields are charged under U1 gauge times spin 3 mod Z2. And that mod Z2 is responsible for the gauge field A being a spin C connection with which can have pi fluxes in the presence of W2.
I'm still confused. If the fermions are doublet under SU2F, they also transform by a -1 under the center of SU2F.
They do, but again, that's a gauge transformation. Again, that's a gauge transfer. That I'll discuss. So right now, I answered your question about spacetime. We'll move on to SU2F, and I'll say something about SU2F as well. But does that answer your question about the spin?
Yeah.
Okay, great. So let's now talk about SU2F, and indeed, there's going to be a discussion about the center of SU2F. So there's an interesting kind of dichotomy in the kind of local operators of this theory. They break up into standard conventional field polynomials or non-monopoles and monopoles. So the monopoles will be the heroes of my story, but let me first discuss the non-monopoles. The non-monopoles are the standard gauge invariant combinations of the psi's and the f's and so forth with covariant derivatives. So for example, we could have a bilinear of the psi's. Actually, there'll be a particular bilinear of the psi's, which will be a very important object in my story. So let me write it. This is an SU2 triplet. So it has isospin 1, which is why I'm writing it with a sigma matrix like this. There's also isospin singlets, which you can form, psi bar psi, for example. These are all gauge invariant. And as Greg said correctly, because the center of SU2F acts on the fermions like a gauge transformation, these conventional local operators do not actually transform faithfully under SU2F. They transform faithfully under its Z2 quotient. And that's related to the fact that these operators are not monopole operators, and therefore they have magnetic charge. Let me call the magnetic charge under this U1 magnetic symmetry QM. They have magnetic charge 0, and therefore, as far as they're concerned, this symmetry group is actually SU2 mod Z2. So it acts like SO3. So only SU2F mod Z2 acts faithfully. And if you only considered these operators, you might conclude that the symmetry of the theory is actually genuinely SO3. That, for example, would be the case if we considered charged scalars instead of charged fermions. However, we also have monopole operators in the theory. So this is not yet the complete list of gauge invariant local operators, right? Monopole operators are operators where you can define them in many ways, but one way to define them is you define them as sort of disorder operators, where you drill a hole in space-time and you put a Dirac singularity for the electromagnetic field there, so that if you consider a small SU2 surrounding this space-time point, you put boundary conditions that say that the magnetic flux across this S2 is QM, or 2 pi QM, or QM is the monopole charge. You can also define them in radial quantization on the sphere if you want. In free Maxwell theory, you can write them explicitly by dualizing the Maxwell field into a compact scalar, and then they look like vertex operators, but you can't do that in a theory with fermions, with matter, so that description is not valid in general. And once you put magnetic flux on the sphere, the fermions, the Dirac fermions, will have zero modes, famously, and quantizing those zero modes can change the quantum numbers of the monopole operator. In particular, they can acquire quantum numbers under either space-time symmetries, they can acquire spin, or they can acquire internal quantum numbers. Then the details depend on the precise matter content in your theory, the Chern-Simons level, if any, for us it's 0, and the monopole flux. So it turns out that when you solve this problem, has been analyzed in a lot of detail over the years, and when you look at this particular case, what you find is that quantizing the fermion 0 modes makes the monopole operator a spin singlet. It's spin 0, it's a scalar operator, but it's an iso doublet under SU2 flavor. So the monopole operator transforms in the fundamental representation of SU2, and because it has monopole charge 1 under the U1 magnetic, it actually transforms in the fundamental representation of the entire U2. This is a U2 fundamental. If you need an analogy, a group theoretic analogy, which might be helpful when we discuss symmetry breaking, if you think of this U2 not as the global symmetry group of my theory, but instead as the standard model gauge group, then the monopole operator has exactly the quantum numbers of the standard model Higgs field. So that'll be useful when we think about what kind of symmetries are broken and unbroken when the monopole gets a VEV.
Sorry, a question.
Yeah.
So, like in pure Maxwell theory, you can just define a monopole by imposing the flux, but in presence of matter field, you should also impose some boundary condition for the matter fields. And here you should impose some boundary condition for the fermions. Is this related with this extension that you're talking about, or is it's another problem?
Extension.
So the extension, I mean that that you have U2 instead of PSU2 times U1. I'm saying the fact that the monopoles acquire a flavor charge, is it related with the fact that
Well,
you have to impose some boundary condition for the fermions?
Well, once you impose boundary conditions for, so there's all sorts of choices involved, and in different ways of defining the operators, you can phrase it differently. For example, if you study the operator in radial quantization, where you consider states on S2, there's nothing to talk about. The moment you say that you have flux, then the rest of the story follows. So also in general, the moment you put boundary conditions for the flux, the Atiyah-Singer theorem tells you that the Dirac operator has zero modes on the S2, regardless of whatever other details might come into play. And so quantizing them will do something. Let me say it differently. Once I've specified my theory, which I've told you in the beginning, what is the Lagrangian, what are the fields, the question of what are the local operators is not an ambiguous question. There's a definite answer to this question. I'm telling you what the answer is, but it does not depend on some random choices. Very good. Okay, so now that I've told you what the symmetries are and what the monopole operators are, and in particular what the quantum numbers of this fundamental charge 1 monopole are. So I should say again, this is the minimal monopole with monopole charge 1. There are also higher charge monopoles, which can transform in more interesting, complicated, non-irreducible representation of the flavor symmetry. I can tell you what our main claim is about QED3. So our main claim about QED3 with 2 flavors is that if it's not a CFT, it spontaneously breaks symmetries. And in particular, the symmetry breaking order parameter is the monopole operator, which will acquire a non-zero VEV. There'll be all sorts of other things going on, which I'll come to, but this is the basic statement. And because I've told you that this monopole is a fundamental of U2, or if you wish, you can think of the analogy with the standard model, when it gets a VEV, the U2 symmetry, or the SU2 times U1 mod Z2 symmetry is broken in the following pattern. It's broken to an unbroken U1 stabilizer broke. All right? So this U2 is SU2 flavor times U1 monopole mod Z2. This where the standard model is U1 unbroken would be the U1 of electromagnetism. And the reason I'm calling it U1 unbroken rather than something more trivial like U1 diagonal or something like that is because the way in which this U1 unbroken would be fibered over the space of vacuum is kind of non-trivial, and that's part of our story, which I'll get to, but let me start with the basics. So we have U2, which is a dimension 4 Lie group, and we're breaking it to U1, so we should get 3 Goldstone bosons. So there are 3 massless Nambu-Goldstone bosons, and they are described by a U2 mod U1 coset, which you can either think of as SU2, or equivalently as a manifold, it's S3. Very importantly, this S3 does not need to be round. In order for the S3 to be round, I need a SU2 left symmetry and an SU2 right symmetry, or an SO4 symmetry. But I only have a U2 symmetry, which you can think of as an SU2 left and maybe a U1 right. And so that means my S3 is actually squashed. As I'll explain in more detail, it's squashed along one of its hop fibers. So I'll call it S3 tilde, which to remind you of that. So a nice way of describing this S3, and which will also be related to other pieces of the physics, is to think about it indeed in terms of the Hopf map. So you can describe this S3 by thinking about the Hopf map from the monopoles, which are the fields that parameterize my S3, to the base of the Hopf map. And the way you do this is you form the following SU2 triplet. You see this combination is neutral under U1 magnetic, and it's a triplet under SU2 flavor. So if you normalize it, suitably normalize it, this is actually a unit vector that I'll call n. N is a unit vector, and it parameterizes the CP1 base of the Hopf vibration. So you see that from the point of view of this base, somehow it looks like there's a unit vector, which is a triplet, which looks like it spontaneously breaks SU2 to U1, which would naturally give you a CP1, but in fact you have this additional Hopf fiber. So let me draw you roughly a little bit what this Hopf vibration looks like. Here's the CP1 base, parameterized by n, the unit vector n, and then over each point of this vibration, there's a compact Hopf fiber, compact circle, which is parameterized by a scalar that I'll call sigma. And so for example, if you're at the north pole of this sphere, let me draw the equator of the sphere a little bit here, right, where the vector n points up like this, then the Hopf circle is parameterized by monopole operators that look like this. So they're basically kind of in the first component of this doublet, whereas if you look at the south pole, when n points down, then the Hopf circle corresponds to monopoles that are in the second component. So I'm just describing here the Hopf vibration, and the fact that these Hopf circles live in different components of the doublet also means that the unbroken symmetry is different. You can check from what I just wrote down that the unbroken symmetry at the north pole is to a factor of a half U1 magnetic minus U1 flavor. We're here calling U1 flavor the cartan of SU2. And here, the unbroken symmetry at the south pole is actually the sum of U1 magnetic and U1 flavor. And the reason for that is that the two components of the SU2 doublet of monopoles have different opposite charges under the U1 cartan. So the fact that this unbroken symmetry is different at the north and the south pole is a hallmark of the Hopf vibration. So it's non-trivially fibered over the base. So this cartan is singled out by the fact that it preserves the unit vector n. Very good. So this is one way of thinking about this squash S3, which is going to be useful. Any questions about this?
Yeah, so this assumed NF equals to 2, but how much would change if you had 4, 6, and so on in this analysis?
Well, there'll be a different coset, right? The flavor symmetry will be bigger. It will not you will always have a U1 monopole, and the SU2 flavor symmetry will be replaced by something SU even. And then the coset will be similar. So there'll be an analog of the CP1 base, which only knows about the SU part, roughly speaking, and then there'll be a non-trivially fibered circle bundle over the space, which will take the place of the Hopf bundle. It's a space that we describe explicitly, but I don't know if it has a standard name.
But it sort of completely carries through And you don't see any difference between the NF equals to 2 case at this level of the analysis.
There are some subtle differences in the anomalies and the anomaly matching because the higher NF cases have slightly different anomaly structures and the topology of the space of the coset is richer. One interesting feature of this S3 is that it doesn't have any 2 cycles. And you know that's not the case for the higher NF cases. So the type of topological terms that you can write in the sigma model is slightly richer in the higher NF case than it is in the NF equals 2 case. But apart from that, the whole story carries through. But this is why I was saying that the NF equals 2 case is also the simplest, because it's a space you recognize more or less immediately.
By the way, did you draw these yellow lines onto the screen? I have a hunch that somebody else did. Whoever did
I don't think
this,
so, because I don't have yellow in
yes,
my
but
palette.
whoever did it,
palette.
could you please undo this? Well,
they may not have realized. So
yeah, I think they may not have realized. You're all out of Zoom practice. No.
All right. Very good. So I've so far only explained our claim. I have not explained where it comes from. And I will do that in the last part of the talk. So in the last part of the talk, I will try to explain how you actually argue for this symmetry breaking scenario, using mass deformations and various restrictions coming from the Vafa-Witten theorem and things like that. But if you take that scenario at face value for a second, I want to make a little bit of a detour into anomalies and anomaly matching.
Sorry, can I ask a question?
Yeah.
I didn't get if this is the only possible scenario apart of CFT, or you can have other symmetry breaking patterns.
Good. So that's one of the main points of our paper. One of the main points of our paper is to argue that this is the only alternative to being a CFT.
Okay.
There are other logical alternatives at the level of group theory and at the level of anomaly matching, but we argue that dynamically in the theory that I explained, QED3 with no extra bells and whistles, this is the only alternative.
Okay, thank you.
So that's a statement that's stronger than kinematic constraints like anomaly matching. It's a statement about the dynamics of this theory.
Presumably, you're going to tell us the logic that goes into that. What are the?
Yes. I will sketch the logic. So as the logic will basically involve studying mass deformations of this theory. So there'll be a phase diagram that depends on these mass parameters, and then I will be able to basically argue what the phases look like as a function of the mass, and then I'll take a limit as m goes to 0, which will recover this scenario. All right. But before I do that, I want to do a little brief detour about anomaly matching because I haven't yet argued to you that the scenario that I just wrote down is actually compatible with anomaly matching. So I have to do that, and then I have to explain to you how the anomalies are matched, which is somewhat interesting in this case. So this is I certainly need to do that if I want to claim that this is a consistent scenario, but it doesn't, although it doesn't establish it dynamically. So it turns out that the anomalies of these theories are pretty simple to characterize. There's a kind of anomaly whose 4D inflow action or symmetry SPT or whatever you want to call it. So the invertible 4D TQFT that characterizes the anomaly is given by the second Chern class of the U2 background fields. And in general, this Chern class is multiplied by some theta angle, and the claim is that the anomaly corresponds to theta equals pi. So this is an anomaly of time reversal type or of parity type. In other words, if we didn't have time reversal, then theta would be a continuous parameter, and this would not be an anomaly. Because there would be no non-trivial deformation classes. But if we insist on time reversal, then theta is quantized to be either 0 or pi. And the case theta equals 0 is the trivial case, and the case theta equals pi is a non-trivial time reversal anomaly or parity style anomaly. This is very similar to the parity anomaly of free fermions, except that here the symmetry group that appears is not just the sort of SU2 part of the symmetry that acts on the free fermions, it's the whole U2 that includes both SU2 and the U1 magnetic. And an interesting fact is that this anomaly is non-trivial even if you restrict the SU2 to its U1 cartan. So if you restrict U2 to its cartan, this anomaly does not trivialize. And instead what you get is a theta angle for U1f. So you basically get theta f and theta m are both pi. The theta angles for U1f and U1m are both non-trivial. Sorry, maybe one of them has a minus sign. I don't know if that matters, modulo 2. This is just a statement about how you decompose C2. Very good. So this is a mixed TU2 anomaly. All right. So how is this anomaly matched in the sigma model? Well, as I said before, the sigma model doesn't have any 2 cycles. It's just S3, but it does have one obvious and interesting 3 cycle, which is just all of S3, right? And it turns out that the correct thing to do, if you want to match such a theta angle in the 4D theory, is to take your 3D sigma model, your S3 sigma model, and add to it a theta term, which is simply the pullback of the volume form of the squashed S3. So this is the unit volume form on the squashed S3, the generator of H3 with integer coefficients, and here F is the map from spacetime to the squashed S3. So it's just the sigma model field, which includes N and also the Hopf fiber. And when you normalize the term like that, it turns out that it precisely matches this anomaly. This is a little exercise in equivariant cohomology, or in the language of background fields. If you turn on background fields for the U2 symmetry, this object will become covariantized, and it will no longer be invariant under U2 background gauge transformations, and its non-invariance is precisely captured by C2 of U2. So this is a little exercise in equivariant cohomology that one can go through. I will not explain how it works, but I will actually explain a different approach to getting the same answer in just a second. But the upshot is that you need to include a theta angle in the sigma model with theta equals pi. Yes, is there a question?
The question, should I think these two thetas to be the same? For instance, if I break time reversal by adding masses, and in principle I can have other values of theta in the sigma model, should I think that I also have to add a theta term in the bulk with theta different from pi?
Well, I think that's a matter of taste, I think. But you certainly can. If you want to regularize your theory in such a way that it's fully invariant under all the symmetries, then it's a good idea to add the bulk, even if theta is not 0 or pi. But you don't, strictly speaking, have to do that. There's also no more anomaly if you consider only fixed values of theta. If you allow theta to evolve in a family, then there's still an interesting anomaly. But if theta is some random fixed value which is not 0 pi, then there's no anomaly.
I'm also slightly confused about a related point. As you mentioned, this theta angle in the bulk is an anomaly for time reversal only for theta equal to pi. Of course, if there is no time reversal. I can have more values of theta. But
That's
when I
actually what
don't,
happens, by the way. When you do exactly what you said, when you turn on a time reversal breaking mass, then theta will start evolving away from theta equals pi.
okay. But then how should I think about this term in the bound? Okay, if it is not an anomaly, and I understand it is not an anomaly because it is a tunable parameter, how should I think about it?
Well, you can think about it if you wish. One way of thinking about it is exactly in the same way that I just wrote. So you can still have this bulk C2 Chern class if you want, and it'll absorb the gauge transformation properties of your three-dimensional theta term, so that is a nice way of presenting the theory under which U2 gauge invariance is manifest.
Okay, I see. Okay, thanks.
Hey, Thomas, I have a follow-up question following Sakura's earlier question. So for the higher N, can you comment on how the anomaly matches for higher NF? In particular, the target space won't be a three manifold anymore, right? So
that's true, but it will have all sorts of. It will not be a three manifold, but it will have all sorts of cycles. And it will be an odd dimensional manifold because you always have some kind of like complex Grassmannian as the base, and then there's a circle fiber. So I cannot recall off the top of my head all the theta terms that you need to turn on, but I will give you an easy deformation argument in this model that will prove automatically that all the anomalies are matched. And such a deformation argument also works for all the higher NF cases. Yeah, but indeed, spelling out all the different theta angles and Wezzo-Mino terms that need to be turned on is a little bit non-trivial.
Okay, thank you.
Yeah, so the thing that I mentioned in answer to Sakura's question is that for an F bigger than 2, there's a new phenomenon which didn't happen here, which is that you start having Wezzo-Mino terms. And Wezzo-Mino terms are associated with degree 4 cohomology classes in 3 dimensions, right? And which S3 doesn't have, but these larger spaces have. So the anomaly matching is kind of shared between these different terms.
I see. Okay, thank you.
All right. So let me say a few words about anomaly matching, and then I'll try to come back to the actual argument for the phase diagram of QED3. I should go a little bit more quickly because I see I only have 15 minutes left. So, when you try to convince yourself that a certain dynamical scenario is consistent with anomalies, without necessarily proving that it's what the dynamics does, it's very useful to realize that scenario in a completely explicit fashion at weak coupling. So for the next 5 minutes or so, I'm going to take my QED3 theory and I'm going to explicitly change it. I'm going to add new fields. I'm going to add new interactions. So I'm no longer discussing the same theory we started with. But that argument will be useful in order to convince ourselves of how anomaly matching works. So I'm going to start with QED3. The theory I'm actually interested in is the RG flow of that theory, just QED by itself, which I've argued to you gives this squashed sigma model. And because the theory is strongly coupled, the radii of that squashed S3 sigma model are set by the strong coupling scale, which is E squared. What I'm going to do for the next few minutes is I'm going to explicitly deform this theory. I'm going to add an extra scalar field, which is going to be neutral, and it's going to be an iso triplet. And then I'm going to couple this scalar field in a kind of Yukawa-like fashion to this SU2 triplet order parameter that I called O previously. So I'm adding some kind of Yukawa couplings. In condensed matter physics and early high energy literature, it's often the case that people integrate out this phi and then they say that you deform the theory by a quartic operator in the fermions, but that's not something that makes a lot of sense in continuum quantum field theory. So I'm going to stick to this presentation with the extra scalar field. And then by giving a potential to phi, you can engineer a scenario in which this scalar field gets a VEV, And in particular, this VEV could be huge, could be much larger than the strong coupling scale, so that the symmetry breaking happens at very, very weak coupling in a completely controlled regime. And then what you learn, what you will get is that you will get a CP1 sigma model whose radius is phi, and the fiber radius will still be E squared, because the fiber radius comes from dualizing the Maxwell field to a compact scalar, and that's just given by the value of the Maxwell gauge coupling. So you'll also get a squashed S3, but the ratio of the radii is very different, but that doesn't matter as far as the symmetries and the anomalies is concerned. Incidentally, this is a model that was considered in all sorts of different communities for different reasons. It was considered in the early 2000s by Senthil and Fisher in the context of condensed matter applications of QED3. And if you look back even further, the same model appears in disguise in the work of Zyberg and Witten on QED with n equals to 4 supersymmetry in 3 dimensions, because this scalar field that I'm adding is literally the scalar superpartner of the gauge field in an n equals to 4 vector multiplet. So they also had a Hopf vibration and a very similar looking story. Very good. So in this weakly coupled setting, you can now completely explicitly analyze what the theory does. You see, the moment phi gets a VEV, the fermions acquire a very large mass because of this Yukawa coupling. Then you can integrate them out at one loop, and you can derive the low energy effective action for the model. And the only low energy degrees of freedom are the angular degrees of freedom in the scalar field, which parameterizes this unit vector that gives you the CP1. And there's also the photon, which when you dualize it will give you the Hopf fibers. And before you dualize, the low energy effective action looks something like this. You get a CP1 sigma model with radius given by the VEV of phi. You'll get a free photon. And then, very interestingly, integrating out the fermions in the background of these other light fields generates a kind of Chern-Simons term between the photon and the pullback of the area form of the CP1 sigma model.
Shouldn't it be an 8 invariant?
Yeah, so you're getting to you're correctly anticipating that what the formula I just wrote is incorrect. It doesn't actually make any sense. It needs to be completed by a bulk term, which one way of thinking about this bulk term is from the eta invariant.
Okay.
And so this is sloppy and imprecise, and making it more precise will be related to anomaly matching. So let me just write this formula, because this is the formula that you can naively get by integrating out the fermions locally in 3 dimensions. So these were formulas that were derived by Abanov and Wigman in the late 90s. And this formula has a nice interpretation, which is that this pullback here of the CP1 volume form is the skyrmion current of the CP1 sigma model. And the skyrmion current of the CP1 sigma model gives charge to some kind of local particles. And this current is gauged by this Chern-Simons term under the dynamical spin C connection, right? So roughly speaking, you can think of the skyrmions of the CP1 as the remnant of the electrons. And in fact, if you ungauge the U1 symmetry, that's exactly what you will get. And here it's gauged by the photon. So somehow the skyrmion current is destroyed, and that's good because we don't have such a skyrmion symmetry in QED. Okay, so in the interest of time, I might say some of the things I wanted to say in more detail in words, but in partial answer to Greg's question, this term is ill-defined for all sorts of reasons. One of the many reasons it's ill-defined is that A is a spin C connection, so it can have half-integer fluxes, and therefore this is not a properly quantized Chern-Simons term. But there is a way of properly defining it by extending it into the bulk. So let me very briefly write down the relevant formula. So this term here can be defined by extending M3 to a 4-manifold and then extending both the CP1 fields and the spin C connection A to this 4-dimensional bulk. And you can check that in the usual style of these arguments, these extensions don't matter. This is a genuinely 3-dimensional term. I won't go through that algebra. It involves a bunch of half-integer fluxes ultimately canceling in the final answer. But an important part is played by the fact that the CP1 model doesn't have by itself a degree 4 cohomology class in 4 dimensions. So if you take omega wedge omega in 4 dimensions, you get 0. And it turns out that you can then show that the effect of this 4-dimensional or seemingly 4-dimensional term on the 3-dimensional path integral is to give you a phase which is -1 to the Hopf number of the CP1 field. And this -1 to the Hopf number of the CP1 field is precisely the theta equals pi term from the point of view of the S3. Right? The theta equals pi term from the point of view of the S3 only gives you a sign in the path integral. It gives you -1 if the winding number of the S3 is odd and +1 if it's even. And that's accounted for in this presentation by this -1 to the Hopf number. Very good. And the last thing I will say is that if you now go ahead and dualize the photon into an ordinary compact scalar, you reconstitute the S3 sigma model that I had before. It's clear that you already have the CP1 base. Dualizing the photon will give you an extra compact scalar. And I think, as already noted, for example, in the supersymmetric Seiberg-Witten paper, this Chern-Simons term upon dualization gives you the Hopf vibration. So this is a very straightforward exercise in abelian duality, which is spelled out in our paper and also in these other references. Okay, so in the last few minutes, let me try to give you a flavor for how we actually tackle not this weakly coupled deformation of QED, but QED itself. So this argument that I just gave you shows you that the S3 squashed sigma model with theta equals pi is consistent with anomaly matching because it resulted from an explicit deformation that breaks no symmetries, completely symmetry preserving. So as far as convincing yourself that this is a scenario that's consistent with anomaly matching, that's sufficient. But the question is, what about undeformed QED3? Why does it do this? Okay, so let me sketch for you the argument. Maybe depending on how far we get, we can relegate some of the discussion to the questions. So the idea, of course, in this model, I don't have this triplet field that I can use to go to weak coupling. So I have to do something else. And the other thing that I can do is I can explicitly turn on parameters. So the theory that we started with, which has only the fermions and the photon, has mass deformations. And in particular, you can deform the theory by adding this triplet mass to it. So you can explicitly add something like m dot O to the theory. In the symmetry breaking scenario with a squashed S3, this triplet bilinear flows at long distances simply to the triplet vector n that parameterizes the CP1 base with a non-zero coefficient. You can actually show that. This mass deformation is nice. It breaks some of the flavor symmetry. It breaks SU2 to its U1 cartan. But it preserves time reversal, or it preserves some definition of time reversal, which is important if you want to use arguments in the spirit of the Waffa-Witten theorem. In fact, Waffa and Witten used exactly this deformation in their arguments, which I'll recall in just a second. So, in fact, there's a nice observation I can make about this O just before we go on to the rest of the discussion, which is that you see that this O, which is a standard local operator constructed just out of the fermions, also gets a VEV because it's proportional to the CP1 unit vector, right? And in a given vacuum on the CP1, it just points into some direction. So this O by itself also looks like it's spontaneously breaking a symmetry. It looks like it's breaking SU2 to U1. And in many early discussions of this model, people focused on this symmetry breaking aspect. They said, well, this should be kind of like QCD, so there should be some fermion bilinear that gets a VEV, also very strongly motivated by what Waffa and Witten did. And therefore, they considered this symmetry breaking pattern driven only by this bilinear. And what actually happens in our proposal is that the symmetry breaking is more complicated. It's if you wish, it's primarily driven by the monopole operator, but as a kind of secondary consequence of that, the triplet also gets a VEV, and that VEV is exactly aligned with the cartan that's already picked out by the monopole. Right? The monopole selects out an unbroken U1, therefore it picks a cartan inside SU2, and this n vector is precisely aligned with that cartan. So there's a kind of alignment mechanism where the monopole breaks SU2 to U1, and then this bilinear also breaks SU2 to U1 in exactly the same direction. If they were misaligned, you would break an additional symmetry, and that would lead to an additional Goldstone boson. It would lead to 4 Goldstone bosons, they're not 3. And that doesn't happen. Okay, very good.
Sorry, are the scales of the VEVs the same?
Sorry?
Are the scales of the two VEVs the same?
Oh no, they may be different, presumably by some order 1 factor. There's no simple formula that relates them, but I claim that they're both non-zero and aligned.
Okay.
Very good. So let's add this deformation, and for concreteness, I'm going to add it in the kind of sigma 3 direction, right? I'm going to pick the triplet mass to be pointing in the sigma 3 direction. So this is if you wish, psi 1 minus psi 2 psi 2. So it gives positive mass to one fermion and negative mass to the other fermion. Very good. So what happens when you do that? Well, when you do that, let's go back to our squashed S3 presentation in terms of a CP1 base with a hop fiber over the various points. Right? The first thing that will happen when you add this deformation is you pin the vector on the CP1 base in a way that's aligned with the triplet mass. So for example, if you take M to be positive, then you are pinning yourself to this vacuum on the north pole of the CP1. And that means that in particular, the CP1 fields get masses. So the CP1 is lifted by this deformation. That's kind of standard symmetry breaking. The fermion bilinear gets a VEV, you add that operator to the Lagrangian, and then the mass lifts the sigma model. But importantly, it doesn't lift all the Lamb-Goldstone bosons, right? The compact scalar, which parameterizes the hop fiber over the north pole, remains massless. This bilinear only gives mass to the CP1 fields on the base. So when you turn on M, this mass M with a very tiny coefficient, what you learn is that you get a free compact scalar, or nearly free compact scalar, which when you dualize it becomes a free photon. So the moment you turn on any small mass, you are in a Coulomb phase with a nearly free photon plus higher derivative corrections where the U1 magnetic symmetry is spontaneously broken. In fact, the more precise statement is that the moment you turn on this triplet mass, the symmetry that's preserved is this U1 North Pole symmetry, which is a linear combination of U1 flavor and U1 magnetic. And then this U1 North Pole symmetry is further spontaneously broken to give you the massless photon. So what I've just described is the analysis in the sigma model for very small m. I've assumed my symmetry breaking scenario, and I've told you what happens for very small m. you can now crank up M, and in principle, you can study all intermediate values of M. But the first thing you can ask is, does this picture agree with what happens at M equals infinity? Right? If you make M very large, then we're back in a weakly coupled regime, because then the electrons are very heavy. You can integrate them out, and you also get a free photon. And you can ask, is that free photon the same free photon that I saw in the small m regime? And by what I mean by that question is it a Goldstone boson for the same spontaneously broken symmetry? And the answer is yes. Right? You can do this exercise explicitly. You can now go to the large M limit, much bigger than E squared, integrate out the fermions, and then you're left with a free photon with an effective action that looks something like this. It's just, Maxwell plus higher derivatives. That's what makes it a free photon. And then it has interesting Chern-Simons terms to background fields. It couples to the U1F symmetry, and it couples to the U1 magnetic symmetry. Here AM and AF are background fields for U1M and U1F. And this term is kind of fixed from the way that we've defined our normalization of U1M, but the coefficient of U1F is interesting. It's basically plus or minus 1, depending on the sign of the math. So for positive M, which is the case that we've been considering right now, it's positive. What do these terms tell you? These terms tell you exactly which linear combination of symmetries the monopole operator of the free photon theory is charged under. If you make a little monopole operator with Dirac flux for the photon, this term tells you that it carries AF charge, and this term tells you that it carries AM charge. And when you compute those charges, you'll find that they're precisely the charges of the monopole that condensed in the small m regime. So you have a kind of continuous picture where both the small m regime and the large m regime are a Coulomb phase, where the same monopole condensed. So you have a kind of array and isotriplet space along which the symmetry breaking pattern is constant. Okay, so the fact that the small m and the large m regime are the same is good. That's very encouraging. That should somehow lead us to conjecture that there's no phase transition in between. And in fact, that's what we argue in the paper. We argue that using positivity theorems like the Vafa-Witten theorem and its friends, you can very plausibly argue that for all values of M, including the intermediate strong coupling regime, the only thing you have at low energies is a single photon, a Coulomb phase with precisely the symmetry breaking pattern. If there's some interest in explaining that, I can say a few more words about it in the questions, but that's really the main idea I wanted to get across. So the moment you have established the symmetry breaking pattern, right, along these rays, you have now these incoming rays in M space that go into the origin. And along each ray, you have a symmetry breaking pattern that singles out a particular U1 hop fiber over the CP1 base that's correlated with the angle of approach into the origin. So once you've established this picture, you've essentially established the hop vibration at infinity or at finite radius. And then when you take the limit back to the origin, you can argue that it reconstitutes the squashed S3 picture that I spelled out for you. Now, there's all sorts of scenarios that you need to kind of rule out in order to prove that this is the only thing that can happen. Why is it that when I take the limit to the origin, the whole symmetry is spontaneously broken? Why can't it be that maybe some subgroup remains unbroken or something like that? Well, it turns out you can argue against that by essentially always doing the same thing. You take any scenario that you want to rule out, you hit it with a small mass deformation, and then you see whether you land in a Coulomb phase. So the criterion that I'm using is that for any small mass deformation, I land in a Coulomb phase with no extra degrees of freedom around. So let me give you an extreme scenario just to kind of point you in the right direction. Let's imagine you didn't know about anomaly matching, and then the dumbest possibility is that the infrared is just a gap theory. That's inconsistent with anomaly matching, but let's forget that for a second. The moment you have a gap theory, then you know that this cannot possibly be consistent with the idea that turning on a small mass will give you a photon, right? Because if you turn on a small mass in the gap theory, that just doesn't do anything. So this constraint that even adding a tiny infinitesimal mass leads to a Coulomb phase is actually very restrictive. Okay. Very good. So as I said, I'm happy to elaborate on all of these points that I was a little bit short about at the end, but maybe in the interest of time, let me just summarize the main conclusions, and then we can move on to questions, if that's okay. So the main summary is that QED3 with 2 flavors spontaneously breaks SU2 times U1 monopole mod Z2 to a U1, to an unbroken U1. And the symmetry breaking pattern has the monopole order parameter, which is sort of the primary driver of the story. And then it has an associated bilinear VEV, which is precisely aligned with the monopole via the Hopf map. And one of the many reasons I'm emphasizing this point is that an enormous amount of discussion in the literature centers only on this observable, has completely ignored this, including a lot of lattice papers and so forth. And very importantly, if you believe in this scenario, it's very confusing what the right number of Goldstone boson is. If you're naive, you might think there should only be 2 Goldstone bosons in a CP1, and instead I've argued that there should be 3 Goldstone bosons, which are the CP1 fields plus the photon, non-trivially fibered in this squashed S3 sigma model. Right. And there's an interesting question of how one might look for this scenario on a lattice or in numerics, and exactly, what kind of symmetries one needs to preserve in order to see it. So I'm happy to say something about that as well if there's interest. But let me stop here.
Great, thanks very much. I think Thomas was a really nice talk. Other questions?
Sorry, would it be logically possible, at least like naively, that the fermion bilinear don't take a VEV at all?
It's logically possible, but you can rule it out using the small m deformation argument. So let me sketch the argument. You can ask a very similar question about QCD. In QCD, the chiral symmetry is spontaneously broken, but you could ask if for some miraculous reason this could happen without the bilinear getting a VEV. And in both cases, one can argue that the answer is no. And the reason that the answer is no is because the Vafa-Witten theorem tells you that the moment you turn on this triplet math, the moment you turn on this is what I called O in the Lagrangian, the CP1 fields have to be lifted. All the arguments of the Vafa-Witten theorem work roughly the same way. What Vafa-Witten established is that assuming a whole bunch of things, including positivity of the Euclidean functional integral measure, which is consistent with this mass deformation. So you have measure positivity. What they did is they established a very interesting kind of uniform bound on the electron propagator in a background field. So if you take the electron propagator in position space and you study it as a function of fixed U1 background, later we'll integrate over A, but if you just study it like that, then this thing is uniformly bounded, uniformly exponentially bounded by M. This fine print, you have to smear things a little bit to make it precise, but this is roughly what they said. So that if you consider the electron propagator, the gauge non-invariant electron propagator in a fixed electromagnetic background, it decays exponentially with a rate that's driven by this M. And this M is really this M. It's exactly that parameter. It's not something else. So because this bound is uniform, you can then use it underneath the positive definite functional integral and derive interesting bounds in the full theory. And for example, if you can apply this bound to the correlation function of J plus and J minus in the sigma model. Right? The CP1 sigma model has a triplet of currents, J plus minus and 0. J0 being the unbroken one. And you can consider the correlation function of J plus and J minus. And you can use this exponential bound for the propagator to exponentially bound this correlation function by 2m. Why 2m? Because each J contains 2 fermions, and if you contract the fermion propagators, you'll get 2 propagators. So this thing is exponentially bounded with mass 2m. So what does this tell you? This tells you that the moment you add this mass to the Lagrangian, the CP1 sigma model fields can no longer be massless. Right? Because these currents are built out of the CP1 sigma model fields. I mean, they're basically, they're basically d mu and plus minus. And this gives you an exponential bound, which means they have to be massive. In fact, they have to have masses of order m, linear in m. And so this is exactly the analog in this theory of what is usually called the Gelman-Oakes-Renner relation in QCD. So the statement that the pion mass squared is linear in the quark masses.
Let me understand the logic. If the mass, if it were gapless, then the correlator would algebraically decay, which would be much slower decay than this exponential bound. Is that the idea?
That's the idea. That's exactly right. And so what this tells you that these CP1 fields need to acquire masses of order m, and this is only possible if this fermion bilinear actually flows to a non-zero constant times n. So this is a kind of non-perturbative proof that this bilinear actually does need to get a VEV. And I should say that
question. Oh, sorry.
I should say that the other parts of the argument, namely extrapolating between large and small m in the strong coupling regime, which I didn't explain in detail, also follow from these kind of arguments. So in other words, we study the kind of Vafa-Witten type bounds as a function of m and look at the intermediate regime.
So I have two questions. The first one is kind of related to the previous question I asked is, if I understand correctly, the main point of the project is that the NF equals to 2 phase is very different from the large NF phase for QED. But
yeah, provably.
But can you just remind us again, in all this analysis you did, what actually sets apart the NF equals to 2 case versus the large NF case?
Okay, so the thing that in large N you can simply prove that there is no symmetry breaking. You can just analyze the theory and you get a CFT and there's no symmetry breaking. The U1 magnetic is unbroken, the flavor symmetry is unbroken, everything is fine. So the thing that sets this apart is that somebody else, not me, somebody else came and told me that the NF equals 2 theory is not a CFT. I need this input.
Oh, I see.
Okay.
So
If you do not have this input, every single constraint that I've said is compatible with a symmetry preserving CFT at the origin.
I see. Okay, thanks. The second question is, at various points you made contact with related discussions in condensed matter systems. So in those systems, the U1 magnetic symmetry may or may not be there. And how much would that affect your analysis here?
Very good question. Yes, and indeed, it's important in condensed matter systems, but it's also important in the kind of high energy lattice papers where they simulate U1 gauge theory on a lattice and they want to look for symmetry breaking. So the answer depends crucially on how much of the symmetry is preserved, right? So you can make a little wish list of things that you do or do not want to preserve. If you want to break the U1 magnetic symmetry completely, as is generically the case, in condensed matter and on a lattice, unless you have some lattice symmetry that forbids the charge 1 monopole, but generically the charge 1 monopole would be allowed. And then it could just be that the charge 1 monopole appears explicitly in the action. The moment this happens, this is all gone. The entire S3 is lifted, no Goldstone bosons. This is compatible with just a gapped and trivial phase.
Right.
And yeah, you can also see that all the anomalies are gone. So you can also just explicitly add this deformation to the sigma model, and you'll see that it pins you to a point on S3. So you need to have something that prevents this from happening. Maybe you have a certain lattice symmetry, for example, that prevents the minimal monopole. Maybe you have a construction on the lattice that preserves the U1 magnetic symmetry. So for example, this is not particularly natural in condensed matter, but you can do it if you're interested in just Monte Carlo simulating this theory. You could have some kind of modified Villan formulation of the U1 that preserves the U1 magnetic, right? Or so you can either preserve the U1 magnetic, or actually, relatedly, you can study the QED with gauge group R, which is just as good. These two are related by some kind of flat gauging. And in that case, the monopole operators cannot appear in the action. Then there's an interesting question of whether or not, so you preserve the U1M, that's good. So that means that at the very least, you'll have some kind of like photon that you can go after. There'll be like a massless photon. But generically, there would not be the other Goldstone bosons, because even when you preserve the U1 magnetic, the SU2 flavor symmetry is actually a chiral symmetry, right? If you wish, this SU2 flavor just by itself still has like, interesting parity style anomalies. And so it's kind of realized chirally on these. I hesitate to use the word chirally, but you know what I mean. So there's still a problem with preserving this full SU2F symmetry on the lattice. So the dumbest generic thing that would happen if you don't do anything smart is that you would just see the U1 cartan. And if you break SU2F times U1 to just the cartan, the only thing that will remain is the photon. Because breaking SU2F generically lifts the CP1. So generically, you would only see the photon. If you want to really see the 3 Goldstone bosons, you have to work harder to preserve the SU2F, at least approximately.
I think I intuitively understand why the SU2F is kind of chiral in quotation marks, but I'm just curious, can you make them a little bit more precise?
Well, let me just say that if we were in 4 dimensions or thought of full Dirac spinners, it would certainly not act on the whole Dirac spinner, right? So a 4-dimensional Dirac spinner would be combining psi1 and psi2 in a single 4-component spinner. So in that sense, it's chiral.
But why do we want to refer to the 4D physics?
No, we don't. We don't. But let me say this. It's incompatible, for example, with Vafa-Witten type deformation arguments. The moment you give a small mass to the electrons, you cannot preserve this SU2. So.
Okay. All right. Okay. Thank you. This very, very interesting talk.
Great. So I think let's thank Thomas again, and then we can do more questions offline.
Thank you.
Thanks very much.